So welcome to the third session today. My name is Sasha Živković, and I'm an assistant professor of architecture at Cornell University. And I will be moderating this session because, unfortunately, Glenn Wilcox cannot join us as a moderator today. And I very much look forward to the three presentations, which will all revolve around aspects of academia and industry collaboration. Our first presentation is titled Additive Manufacturing for Geometrically Complex Concrete Formwork by Manya Age Mebodi and Fabian Meyer-Bertz. Manya is an assistant professor of architecture at the University of Michigan Taubman College. Her research focuses on developing computational design methods and innovative ways of employing digital fabrication to create smart building elements. Today, she will present a project she has been leading at the Digital Technologies ETH Zurich. Fabian is the head of 3D construction printing at the Burry GmbH in Germany, one of the largest manufacturers of formwork and scaffolding solutions in the world. Fabian's work revolves around paving the way for a broader application of 3D printing in industrial practice and bringing state-of-the-art technology to real-world construction sites. Please help me welcome Manya and Fabian.
Thank you. Yeah, thank you. We're going to make this very short. Concrete is used dramatically in every project. In fact, it is the second most used material after the water, and it is the source of about 8% of carbon dioxide in the world. In the next 80 years, we're going to build more than 2 billion new homes. We are asking how to do it without sinking our planet. We should be using less concrete, obviously. This is not very easy because the way we build today is just like the way we used to build 100 years ago. Basically, we are facing a challenge of fast-growing building industry with lack of digitization.
Here we see a quick example of what formwork looks like in its most innovative fashion. It's a lightweight formwork that can be used for basically every application, be it walls, slabs, or foundations. But we see that this is a standard formwork. While it's modular and can be configured, the shapes are still rather straight, and we use a lot of concrete. If we go to more complex projects like the National Veterans Memorial Museum in Columbus, Ohio, then we see how complex formwork shapes get. So we can do more complex shapes, but then it gets exceedingly expensive a lot of time, and it's not applicable to a very large variety of projects.
So we are working to overcome these challenges. We are working at the intersection of computational design, CNC fabrication, and material processes. 3D printing is a game changer. It's going to change the way we're going to design and build in future. Because it builds material layer by layer, it offers unprecedented freedom of form in high resolution and mass customization with no extra cost. So in the next projects, we will show you how we use 3D printing to augment the large-scale manufacturing of concrete elements and the construction of concrete itself.
So one approach that one can take, and that was spoken about in several presentations along the day, is the printing of concrete itself. So one can imagine if we figure out how to do this in a large scale, and we also figure out how to actually put reinforcement in an automatic fashion in that, we as a company that produces formwork, we would have a big problem. Hence, we've been active in this field for quite a while and want to push this technology forward. This is a picture of the first 3D printed building in Europe, which was done by a company called 3D Printhuset in Denmark. They are now called a company called Cobot, which Burry invested in a while back. And ever since, we've jointly been working on how to make this technology happen in a broader scale. This was 2.5 years ago, actually, and at that time, it took us 2 months to do this small house. And I just want to show you very quickly where this has been going. I mean, we've talked about 3D concrete printing in several presentations today, so I don't want to spend too much time on that. So I just touched up on that 2.5 years ago. It took us a couple of months, and the machine was a prototype. The cabling was a mess. The machine hasn't ever heard of any safety features. And now we come to this machine, which is now a safety-certified machine that automatically calibrates itself and has all the nice features that you want from a full-fledged industrial machine. And we did the same building, and it took us 3 days, and we believe if we would do it a third time, it would take us about 10 hours to do that. So it's really about bringing this to a more industrial scale. We're going to put one of these printers, after we have one in Denmark, one in Germany, and one in Dubai. We're going to put one of these big, large-scale printers to the US in the beginning of next year, and are also going to build up a team around using this technology. We have the focus on making contact with the real world as soon as possible. If we stack a couple of layers of concrete on top of each other, that's very nice, but it's still quite far away from having actually a house or a structure. There's lots of other parts that we need to figure out to do that, and that's what we want to do. But these structures, also the size of the printer, they're not really the application of formwork. Formwork is for big, steel-reinforced concrete structures, and here we see less to or no to little reinforced structures. So we need a different approach if we really want to address the challenge of reducing concrete in steel-reinforced structures.
So instead of printing the concrete itself, we focus on employing additive manufacturing for producing the formwork. One of the technology that we've been using both in industry and academia was binder jetting technology. This is, it binds sand layer by layer by depositing the liquid bonding agents. And what you see there is a bonded material. We like this technology because it offers the biggest and largest geometric freedom and resolution. It also exists in the largest scale. This one is Voxeljet 3D printer, 4 by 2 by 1 meter. Basically means we don't have to build a new facility to have binder jetting technology. So the first project I'm going to show you, it's a Swiss pavilion at Venice Biennale, designed by Christian Karetz and realized and rationalized by us at Digital Building Technology. This is not a cave. So this is an interior of Swiss pavilion in 2016 made of concrete, glass fiber reinforced concrete. And you might be surprised to know that a 5-meter high pavilion is made of only 20 millimeter thick concrete. If you scale this down to an egg size, the shell dimension or thickness is less than the egg shell thickness. What you see here is the formwork. We develop computational method to generate the formwork automatically for any given free-form geometry, and this is very significant. You need a lot of computation to be able to produce the formwork for such geometries. This is the back side of the formwork, which is 3D sand printed, and the front side of the formwork where the glass fiber reinforced concrete was sprayed on. Now, I would like to show you 2 other projects where we use computation to design for material optimization and 3D printing to produce the stay-in-place formwork, which was unbuildable otherwise. And these projects are extensively collaborative. We collaborated with research team at material science team. What you see here is human femur that shows where the stresses are. The tissues are placed, basically distribution of the bone tissue in accordance with the stresses within the bone. What we are doing here is, this is the first slab where we design it based on topology optimization, based on 4 load case, basically generating a form for the loads and the forces that exist within the slab. This is the 3D printed formwork. The formwork itself is only 6 millimeter, and after it was like the loose sand was removed, we cast ultra high performance fiber reinforced concrete in the formwork, which then gives us the composite of concrete and sandstone. What you see here is the slab from below, where you can obviously see the material is placed only where the forces are and where the stresses are. While in a solid concrete, with the same bounding, we will need 270 liter of concrete. In this slab, we only use 50 liter of concrete, which basically means we reduce the concrete consumption by 80%. That's a lot. The next slab, which I'm not going to go through the computation as we don't have much time here, is made for tree load case and the tree support. We also couldn't build this one with any other fabrication method than 3D printing. You couldn't do it with milling. It was produced in an hour, basically a magnitude faster than if you would have milled.
So now that Mania has shown kind of the cutting-edge technology, what you can do with a 3D printed formwork, we as a formwork supplier and manufacturer are then left with the nitty-gritty pieces to make this work on construction sites of a larger scale where we don't have highly trained professionals that have been part of the process of design and manufacturing, but normal construction workers that we provide the formwork with, and then they have to kind of figure it out. So there's a couple of these small problems, and one of them is, for example, that whenever we have complex shapes, in some point or another, this complex shape will then merge into a straight line or in a not very freeform shape, maybe a single curved shape. So we will come from a very complex, potentially 3D printed form to a standard formwork panel. Usually what architects and designers then would like to see is that the concrete surface is of the same color no matter what formwork you've used. However, the formwork has a large impact on concrete color. So this is something that we've tested here with different formwork panels, with different coatings, with, for example, epoxy resin or polyurea coatings on wood and on 3D printed parts. And so we had this nice little checker pattern going on and tried to use that as a formwork. And also what always comes up is, I mean, now we've had a couple of examples of slabs, but if you want to do a big vertical structure, the concrete pressure is, as you all probably know, is rather high. And the question is, can a 3D printed material even withstand that concrete pressure? The answer is pretty easy. Yes, it can. We've done that a couple of times, so it can also be repeated, which is also important for real-world construction projects. And you can't see the checker pattern, but you can see that some of them, you can't really tell the difference if it was a coated 3D printed formwork piece or a wooden formwork panel. So we can achieve basically the hybrid forms. Another of these small nitty-gritty problems that come up is something very simple. Can you drill it? Can you put a screw in it? Can you glue it? What happens if you put a hammer falls down on the formwork? Can you then repair it? So these little gritty problems we had to figure out, and there's lots of 3D printed materials around, and you have to have different solutions in your portfolio for that. So with the sand print that is epoxy infiltrated, that works very well and really has all the needed properties for use on construction site. We've done that then even further, so we built this big formwork piece and gave it to construction workers and told them, go ahead, connect it as you usually would do it. So we see the double curved structure here coated in white, and next to it, which is only a singly curved structure, is a wooden formwork. And both of them connected then come up to something like this, where we see traditional formwork, which everybody knows how to use, combined with a 3D printed formwork. And what comes out is something like that, where we again see that the formwork color is perfectly fine. The vibration of the concrete, as you might see, was a little bit of a problem. In the real world, this piece would actually have been turned upside down, so it would be a nice architectural piece for our purposes, where we didn't want to put too much rebar in it. If it was just a mock-up, we turned it upside down. So it's a very big piece, and we're actually, so that again shows you that 3D printed formwork can be used for real-world applications.
So FDM is another 3D printing technology that we employed for production of formwork. I would like to show you the work that we are right now doing at Tubman College. What you see on the left side is 3D printed thermoplastic formwork, and the right side, the corresponding concrete elements. We've done this with the students at Digital DMT. And right now we are expanding the research together with Wes Mackey to explore how to develop formwork using robotic, how to explore the material or what kind of material can we really print, what is the scale that we can go for production of thermoplastic formwork.
And again, we thought about how can we use that on site, and what's the purpose of having these thermoplastic formwork panels is rather obvious. We can integrate some functionality and not just design into it. We can integrate cable ducts, we can integrate lighting elements directly in the formwork. But again, it's about connecting these pieces. You can see that it was a rather complex issue, and the thermoplast, if it's not a round shape that we're doing, it would be very difficult in regard to the concrete pressure, but for round shapes it actually worked out rather nicely, and we didn't make a mess. It withstood the concrete pressure. Nobody had to get the shovels out and start cleaning up the concrete. And here you can see the final piece upside down. Why did we cast it out? Again, we wanted to obviously check the part at the bottom if it can withstand the concrete pressure and not print the whole thing.
That's a final piece also. So the last project that I would like to share with you is the first real-world slab made from 3D printed formwork, but also involved multiple digital fabrication methods. This work is to enormous extent is a collaboration. Here you see the team, our industry partner, and the involved leading investigators. We wanted to design a slab that uses material only where it needs it, integrates the building services, also expresses the potential of 3D printing. This is an early sketch of the slab in its context, the fab house. That's the slab in the middle that you see. The slab is 78 square meter, cantilevers from a S-shaped wall. It supports a 2-story timber frame structure right above it. Again, here computation is a key. We developed a set of in-house computation tools to generate rib layout based on the load that comes above, to explore design variation, calculate concrete, and the weight of the slab, which are necessary and significant to communicate with the parties involved in the project. From this model, we also generated all the data needed for fabrication, including the 3D printed formwork data. What you see here is the formwork segment. As you may observe, it's made of many puzzles of different parts. The CNC plywood section, the rebar that are bended previously, and the 3D printed formwork itself in gray. Here you would see the 3D printed parts. We had more than 181 3D printed formwork that came together so perfectly to create one segment for a concrete element. Then for that segment, the glass fiber reinforced concrete was sprayed on the formwork, from which a 20 millimeter shell of concrete surface was created. And immediately right after, we had the assembled timber formwork on top of it. This timber formwork already contained the rebars and post-tensioning cables, which would be then used, the formwork would then be used for casting the concrete for the structural part of the slab. Here you see the assembly of concrete segment on the site. Assembly took only 3 to 4 days. It was quick because everything was very precise. You see how thin the slab is in most part. The slab weighs only 60%, basically 60% less than a normal slab that would stand there instead of this one. You also can see the weight that are prefabricated for sending the wires and the pipes throughout the slab. This is the ceiling side of the slab, and very filigreed concrete details which also express we really reach the limit of what we can do with concrete and 3D printing. If we have time, I run a video. Do we have? Yes, I have another 3 minutes. So.
You still have lots of time.
Yeah, not really. Yeah.
It started at like 8 minutes.
Oh, I see, okay. So here you see the team, the design team, also rationalization team. We did the design and rationalization of the whole geometry together. This is the in-house software that was developed, integrated to the Grasshopper software that we have there. A lot of 3D printing, small-scale 3D printing was happening to explore the form itself and the structural capability of the slab. This is the 3D printer that would print sand, basically sandstone, binding it layer by layer. The darker area is where the sand is bind. And this is the process of sand removal. All the parts are removed from the print box, then the loose sand is removed. The parts are then sent for infiltration and post-processing. All the other sections, which was produced by wood, were CNC laser cut, but the 3D model included both the CNC detail and 3D printed detailing in one file. And here is the assembly in the casting company, where the parts come together perfectly. Again, the handling of these parts are, as you pointed out, very important. Where are the holes? Can we drill into these things or not? Because sand can break very easily. Here you would see the post-processing to make the formwork in a way that you can remove it easily from concrete. The 20 millimeter glass fiber reinforced concrete was sprayed, and then the assembled wood modules were assembled right on top of it. This had to be very quick in order for the concrete to have a great bond. And removal of the sand formwork. These are the final pieces, 11 prefabricated concrete segments, which were sent to the site. So just to summarize this project, we achieved over 60% concrete reduction through form optimization. We achieve a high surface quality, high precision, and we produce a freeform slab from 11 of a kind concrete element. Integral computation is key. The 3D printing alone can't do much. We need to compute. We need to develop design method and design software for these tools. The last slide, which is empty, I would like to say that we have shown multiple projects that were only able, or were only been able to be realized through computational method that we developed. And I would like to emphasize on computation more than just fabrication tools that we have. We have shown that additive manufacturing will bring new opportunity for architecture and architecture element and sustainability in future. This is a very disruptive and radical change that we will have. These new technologies will come with less restriction for design and more freedom, yet it will demand from us designers to develop sufficient fabrication and computational method to exploit the potential of these technologies. We are also in a very exciting time. There are a lot of changes. There is an urgent need to rethink the way we build. At the same time, we have a lot of technological development and advancement. It's a great time to explore, play, experiment, and I'm sure our exploration will have a significant impact on the direction that our field will have in future and our planet itself. Yeah, thank you.
Thank you.
Okay, thank you very much. The second presentation today is titled Moving Mass by Brandon Clifford. Brandon is the director and co-founder of Matter Design and an assistant professor at the Massachusetts Institute of Technology. He mines knowledge from the past to design new futures and is best known for bringing megalithic sculptures to life to perform tasks, and he will let us know about that right now. Please help me welcome Brandon.
Yes. Oh, thank you. Hello, everyone. Thank you, Sasha. That was very nice. Today has been pretty amazing so far. Thank you for the opportunity to come here and speak with you. We've seen incredible collaborations between the academy and industry, but also I think very much between the arts and the sciences. There's something special happening here today. I think Wes and Tian, you've done an amazing job. In particular, the first presentation today with Lucia and Forrest. There's something that stuck with me and I think I'll remember for some time, which is the idea of morality of concrete, and that we must think of the afterlife of these things. But in thinking of the afterlife of them, it means that we all of us also must presume that they are alive. So architects operate under the false assumption that we build for eternity with materials that have 100-year lifespans. And this is a topic that I share with great passion with you, so thank you very much. I'm here to present a collaborative project today, which I will get to all the bodies that have been involved in this. While I'm a contemporary designer, the origins of this work are ancient. I've been fascinated with these wonders for the mystery and speculation that surround them, but also for their capacity to force us to think differently. And while there are archaeologists and historians that rigorously address these same precedents, we, as a practice, are not in the game of trying to prove any truths about the past, but we are invested in trying to mine that knowledge to project new futures. So this is an image of Rano Raraku, which is the quarry on Easter Island. You'll notice that these figures are buried halfway up to their heads, and because they are in the process of being transported to their final destination. Take note, they're standing, right? They're staged and prepared for a journey. But this is the image that I think we as Westerners think that the intention of any designer would have for a statue. Its final resting position, its stasis, I would call it its death. When the Dutch explorers first encountered the Rapa Nui, they asked them how their ancestors could have possibly moved these massive statues. And the Rapa Nui said, our ancestors did not move these statues. The statues walked themselves. And for centuries this was dismissed, but it wasn't until 2012 that archaeologists were able to prove that in fact the Moai did walk and they were transported standing, pivoting from side to side. So the statues are in fact engineered to walk by having a precise calibration between the form of the object and the center of mass. They have prescribed a behavior onto these static objects. Megalithic constructions all boil down to two essential principles. These challenges are how things are transported and how they were placed. And I would argue that these are two principles that we as architects today don't address. So for the past 5 years, I've been engaging a very dumb challenge of just getting big, heavy objects to move and stand vertically. Like this 16-foot tall statue designed to walk horizontally and stand vertically. By the way, the impetus of this was a cross-disciplinary collaboration between Mark Jarzenbeck, who's a historian, and myself, asking the question of how can we do a really silly studio project. This is an architecture studio project at MIT. And that raised so many questions for me that we tried to do it again. We produced this floating megalith that swims horizontally under the low bridges of the Charles River and then saturates its belly with the river water to stand vertically. Or for instance, in collaboration with CIMEX Global R&D, trying to get this 4,000-pound behemoth to spring itself to life, to dance on stage. In testing this problem over and over, we started to think about the perception of life in these objects, but also about how humans could engage with these inanimate beings. At this point, you're probably asking, like, what does this have to do with architecture? These are single objects. This is sculpture, art. But by engaging this problem of transportation and erection, we can start to ask the question about how some of these marvels were produced. Because on its own, any one of these stones would have the challenge of transportation and erection, but then layering in other problems, such as raising the stakes beyond that to transportation and placement, getting into logics of assembly and construction. So more recently, we've been asking the question about how we could start to embed the behavior of assembly into the objects themselves. And this is an initiative in collaboration with Matter Design and CIMEX Global R&D. This is the team at CIMEX Global R&D. They are composed of a number of different disciplines, but I think the easiest way to think about this collaboration is that Matter Design is dedicated to form and computation, and this team is dedicated to material science and developing new strategies for embedding intelligence into these matters. So CIMEX is extremely accomplished in innovating in materials, but they came to us to try and look for new perspectives, and I think we've been trying to deliver on that with some strange things. So we joined forces, and we've been just having the simple banner of embedding intelligence into the objects themselves. Okay, so we'll go with this slide. That's fine. There are really only two things that you need to be concerned about in trying to get objects to behave in a manner that you want. There's a center of mass, which I think we can all agree upon. This is an understood principle. But the center of curvature is a little bit more tricky. So let's just begin with the circle. The center of curvature is dead center, the geometric center of that circle. So if the center of mass and the center of curvature are coincidental, you have a wheel. But if you can displace the center of mass a distance from that, you can get that object to wobble back and forth because it produces a riding moment when the contact surface basically displaces those two force vectors. Now, if you get into more complex geometries, such as an ellipse, the resulting, we must have you can see this is the center of curvature for that contact point, and this is the center of curvature for that contact point. So that means that as you roll this thing, the center of curvature is actually moving. The center of mass is obviously staying precisely where it is. But we have to start to think about inscribing behavior by controlling the location of that curve. When we start to think about folding in problems of assembly, we deal with two geometric constraints. One of them is the mobility surface, or the surface that comes into contact with the ground. That's really determining where that contact point is. And the other concern that we have is the assembly geometries, or how things can start to nest with each other to make sure that you don't have collision problems in that process of assembly. When you start to layer in these other complex geometries to get details to nestle these objects together, you start to distribute that location of the geometric center of mass. So we need a way to be able to pull that center of mass back to a precise location. And that's where the collaboration with CIMEX Global R&D has come in, where we're using two different densities of concrete that they've developed in any one of these pieces. So they can hit a range of densities quite precisely, and we use solver computation to essentially move the division plane so that we can pull the center of mass where it needs to be. And in the end, we can produce, here you can see that division plane. Over here is the more dense concrete, and then this is the division plane. But there's this insertion of a tool, and you can see what Matt's doing here is actually providing two possible center of mass locations. So with the tool embedded, you have a wheel, and if you pull the tool out, you have a self-erecting object. And we've been experimenting with a variety of different objects that each have a variety of different behaviors. Some like to stand up, some like to stay horizontal, some like to spin. And we're getting into this moment of thinking about the choreography of how humans can engage with these things. Because ultimately, we're interested in designing not just for the final resting state, but for the complete life cycle of construction. These are, by the way, very heavy. They look light, but they're very heavy. They're solid concrete objects. If a brick is designed for a mason to be able to pick up and place all day long with one hand, and a CMU is designed for two hands, these megalithic constructions allow us to decouple that association between deadlifting objects and the behavior of assembly. So right now, anything above a CMU, the construction industry assumes we're going to deadlift, so we need to start using fossil fuel burning equipment, heavy lifting equipment, cranes, et cetera. And we're wondering if we can start to embed behavior into this, that we could upend challenges such as the tilt-up wall construction. The behavior of these things is quite strange because they have so much inertia that if you just grab them and you try and set them into place, they really don't want to go. But you have to slowly apply constant pressure and guide them into place. So as opposed to thinking of a sweat equity, something that you would be working throughout the day, you turn into a dance partner in trying to manage these things into their position, and it becomes joyful. So here you can see some of the details. We're wondering about a craneless mode of construction where we could impart less energy. And it also means that if we can build in locations that don't have access to cranes, maybe rural conditions, disaster relief scenarios where we have to resort to tent construction as a default strategy to engage. And we're wondering if we can get into some of the principles of mass and thermal properties by lessening the burden of that labor. There's something else that's challenged us, is that because these objects are easy to assemble, that means they're also easy to disassemble. And potentially these objects are not destined for the landfill the way the rest of our concrete is cast. But the real contribution of this work falls outside of conventional evaluation criteria. That empirical evidence as an example. So for the moment, just think back to Easter Island. Because as those statues were designed to walk from quarry to site, there's a notion of spectatorship embedded into that. As spectacular as the Moai are for visitors today, you would have to imagine being there then. Because the real memorial is not the objects themselves, but it's the cultural ritual of bringing a stone to life. Concrete has a life. So in engaging this problem over and over again, we've been doing these experiments. It's really challenging us to think differently about architecture beyond the results and to encompass the entire lifespan, from conception through transportation, assembly, as well as the afterlife. And we did that through a series of very dumb exercises that interrogated ritual, experience, theatricality, and play. By embracing the myth that stones are alive, we were able to reimagine construction, not as a site for labor, but as a site for wonder and whimsy. Thank you very much. I'll just plug one thing. So, by the way, for tonight at the exhibition, I went short, so I'll take the time. We're going to do another experiment called Patty and Jan at the beginning of the exhibition tonight. This is an experiment of megalithic assembly. It will be a performance, and it should be a lot of fun. It might fail, so bring safety glasses. Thanks.
Thank you, Brendan. The third presentation is by Andrew Cudless. Andrew is a designer based in the San Francisco Bay Area, but not anymore, I heard, where he is a professor at the California College of the Arts. In 2004, he founded Matsis, a design studio exploring emergent relationships between architecture, engineering, biology, and computation. Please help me welcome Andrew.
Nice.
There it goes. It's up on the screen.
It won't turn off.
Oh. Just two more. Okay. And it's just the middle. Okay. Thank you. Those last two presentations were phenomenal. And I'm going to show maybe a little less innovative the form work and the movement of those. The last two projects were just incredible. So thank you, Tien and Wes, for the invitation to present at this fantastic conference. I want to begin by recognizing my partners in this project who weren't able to come today to co-present with me. They wrote a paper with me and are basically co-authors on this presentation. So I'm going to read this just to get their words as well as my own. So Tina Florian was the project manager at Lake Flato. Chuck Neves was the project engineer at Architectural Engineers Collaborative. And Josh Zabel was the project lead at Chrysler and Associates. So this presentation focuses on the design, engineering, and fabrication of an innovative tilt-up concrete structure using fiberglass composite molds. The design was produced through a small but multidisciplinary team that valued the integration of form, fabrication, and performance through the application of biomimetic principles, computational design and fabrication, and original construction logics. So the BHP Pavilion is in San Antonio, Texas, and is the central outdoor classroom and community hub of Confluence Park. Let's see, so Confluence Park is here. The actual confluence is here, the confluence of San Antonio River. The city of San Antonio, the downtown, is just up here, and this is San Pedro Creek. There were three primary project objectives that the pavilion needed to satisfy that were driven by the needs of the client, a local nonprofit foundation that leads educational and artistic projects along the San Antonio River. The first objective was to create an educational venue that would integrate the architecture of the pavilion into the educational mission of the park, which was to educate the community on the critical role of water in the regional ecosystem. The second objective was to create an iconic and inspiring pavilion to help catalyze a new identity for this historically underappreciated and underinvested part of the city. Due to the relatively limited budget of the project, the final objective was to use the innovative fabrication technologies and methods to lower the overall project costs while meeting the client's ambitious educational and aesthetic vision. When the final design team first met in, I think it was fall of 2014, the client had already been working on the project for, I think, maybe even 6 years previous to our hiring, and was very eager for the project to be completed as soon as possible. I was actually told, like, we want this in the ground in 6 months. So with their years already on the project, the client was committed to creating a unique educational and community venue, but was also cognizant of their limited budget and the compressed construction schedule. Faced with these challenges, the design team focused on pre-rationalizing the geometry of the pavilion. That is, rather than initially proposing a form that would need to be rationalized in order to be produced, the team focused on several geometric forms and fabrication strategies that already had an inherently rational basis. So during the first week of the design, literally we had 2 days of meetings with the client, 1 day to put a proposal together, and then I presented this to the client. So it was 4 days. The team had developed an initial proposal that used a toroidal surface patch to generate a series of timber beams of varying lengths but with identical curvature. These beams could all be developed from the same glulam mold and then CNC milled into different lengths. The strategy was inspired by several projects developed by Foster and partners that used toroidal patches to rationalize seemingly free-form surfaces. Although the design quickly moved away from using this specific technique, the project team continued to think through the material and construction implications early in the design process in order to better integrate the form, material, and fabrication logics, and hopefully reduce the construction time and budget. At this point in the schematic design, several tensions became apparent to the team. The first was the great need in the project for the central pavilion to reflect the primary mission of the client, and that the initial design of a large timber shell structure did not immediately communicate this mission. That is, the primary stance that most architecture has to water is repulsion. Structures are typically made to push water away as quickly as possible in order to keep the structures and the inhabitants and materials within dry. However, in the context of the San Antonio climate, which has long dry spells punctuated periodically by heavy rainstorms, and the specific context of a park devoted to the educational mission of reconnecting the community with the vital importance of water, it seemed that accepting water into the structure was a more effective strategy. After all, the park was being designed to collect and recycle all groundwater for use in the restrooms and the irrigation systems, so the pavilion could be used to highlight this process. Furthermore, due to the intense heat and sun of the region, the pavilion was primarily sheltering visiting students and community members from the sun, not rain. A decision was made to use the pavilion to celebrate the collection of rainwater and to make the form of the pavilion a pedagogical device for the park's guides and visiting teachers. The form that emerged from this process was based on the doubly curved fronds of many local plant species that cantilever out to collect and redirect dew and rainwater back to the root stem. The double curvature not only gives the cantilevers more strength, but the curvature also creates a channel on the top surface for the efficient flow of water. So within days, the project had moved from a singular large shell pushing water towards the structure's fringes to several funnel-like doubly curved forms that directed the water to an underground cistern for storage and eventual reuse throughout the site. The second tension that emerged at this point was the client's desire for an iconic and unique pavilion in relation to the budgetary need for simplicity and modularity. Although the new doubly curved funnels aligned with the pedagogical mission of the client, the complexity of making these forms initially resisted easy construction strategies. Early designs for the funnel involved complex steel and cable net structures which, even if each was identical, were beyond this modest budget. At this point, inspired by the work of Felix Candela, Heinz Eisler, and many others who had investigated the use of concrete to create complex forms that aligned with structural forces, the team quickly moved to concrete as the primary material. Actually, a funny story about this was I made this rendering in my hotel room the night before a meeting, still while the design was a steel and fabric structure. And I was really nervous because I had already changed the design several times, and I was like, this is too big of a change. And during the next day's design meeting with the engineer, all of a sudden the engineer said, I think the structure needs to be concrete. And I was like, oh, well. and then from then on, you can see this was January 11th, and very quickly evolved. I'll show you in a moment. As the team shifted to concrete, it became necessary to begin to divide the funnel shapes into discrete parts in order to break the forms into manageable parts, while also allowing views into the interior of the funnel. So this was the next day. However, while the earlier steel funnel shapes were designed to cantilever and be supported through tension rings that could balance the forces around the entire funnel, the discrete concrete parts no longer had this tension ring and required a new solution. the design team decided on a simple solution of pairing each discrete funnel part with a symmetrically paired element to create a complete structural arch. This represented a major conceptual shift in the structural organization of the project. Rather than several structurally independent funnel-like forms, the plan was organized into 11 structurally independent arches. Without the tension ring, the project had a new formal freedom, and the funnels could become more open and better communicate the flow of water to the public. The resulting arch is the simplest of structures, the statically determinate three-hinged arch. An arch structure plays to concrete's significant compressive strength while minimizing its limited tensile strength. Referring back to the biomimetic inspiration for the funnels, each half arch was nicknamed a pedal. By separating the pedals with pinned connections at the top of each arch, the team greatly simplified the scope by producing matching pedal shapes with the expressed pins transferring the horizontal stabilizing force between the adjoining pedals. An additional benefit to this new organization of pedals or half arches was the idea of using a modified tilt-up concrete construction technique. Tilt-up concrete construction is defined by concrete panels being cast flat on the ground on site and then lifted or tilted into place and connected to the foundation and adjacent panels. The technique can be considered halfway between cast in place and precast concrete, as the panels are cast on site but not in place. It is a common fabrication technique in the region as it has a very low cost due to the lack of significant formwork. The technique was invented in the US in the early 20th century by Robert Aiken and popularized by Thomas Edison, who in 1908 stated, "Tilt-up concrete eliminates the costly, cumbersome practice of erecting two wooden walls to get one concrete wall." By the late 20th century, some tilt-up concrete fabricators had begun producing curved concrete panels by casting against curved forms dug from the ground or wooden forms built up through multiple layers of plywood. In the context of Confluence Park, tilt-up had a distinct advantage over cast-in-place concrete, as it more easily allows for reusable molds, which can be erected in one place on site throughout the construction process. However, in order to take advantage of tilt-up concrete construction for Confluence Park, the panels needed to be cast at roughly a 45-degree angle in relation to their erected position. This allowed the top surface of the panel to be open to the sky, while the bottom surface was against the formwork. Now that the team had settled on a half arch or pedal concept and the initial material and fabrication strategy, the next task was to determine the exact shape, position, and number of pedals. Returning to the objective of creating a unique and iconic pavilion for the park, the team wanted to make sure that the need for modularity due to the project budget constraints did not create a system that was too geometrically rigid or monotonous. That is, when working with any modular system, it is difficult to escape organizing systems that reinforce the appearance of repetition. Several organizing grids were developed that explored the implications of overall pedal quantity, module quantity, and how repetitive the deployment of these pedals appeared within the grid. The goal was to simultaneously use as few modules as possible in order to reduce the number of pedal molds and increase the casts off of each mold, while also obscuring the modularity of the entire project. This tension between a strict modularity of parts and the overall desire for an informal organization of the whole led us to use an irregular tiling grid. After exploring uniform triangular, rectangular, and hexagonal grids, an irregular pentagonal tiling grid was developed. While the regular pentagons do not tile the plane, and these gaps would have created large unshaded areas within the pavilion, there are 15 types of irregular pentagons that do tile the plane. One of those, type 4, which is also known as the Cairo tile after several streets in Cairo paved with this shape, has 4 long edges of the same length and 1 short side, and a vertex angles of 120, 90, 120, 90, and 120, kind of alternating. When this pentagon is subdivided into 5 triangles by connecting the pentagon center with each vertex, it results in only 3 unique triangles, so 2 A's, so you can kind of see, sorry. So it's a little hard to see, but if you see that pentagon right there, which you can kind of see here, that there's like A, B, and C. So triangles A and B are mirrors of each other, and each have internal angles of 75, 60, and 45, while triangle C is equilateral with all angles being 60. The center of each pentagon represented a funnel drain. So, again, sorry. So like the center of all of these pentagons, which you can see like right there, that would be a drain. down to the cistern. And the edges of the pentagon represented the apex of each arch. Each A triangle is paired with a B triangle from an adjacent pentagon to produce a full arch. And similarly, each C triangle is paired with a C triangle from an adjacent pentagon to create a full arch. In order to produce the final pavilion plan, various selections of A, B, and CC arches were explored and analyzed for the shade produced, as well as the informality of the arches when seen in perspective. That is, the design team tried multiple options of arch arrangements to produce a pattern that, although completely modular, appeared to not line up, and only one full pentagon was formed. In parallel with the selection of the specific plan arrangements, developments of the sectional properties of the geometry were also being developed. There were three primary objectives in developing the section and curvature of the petals. First, for both structural reasons and water flow capture, the petals had to retain double curvature. Second, the thickness of each petal needed to change from bottom to top in accordance with the structural demand, building codes, and rebar placement. Third, the surface curvature should be continuous from petal to petal. In order to test how water would flow on the top surface of the petals, a rainwater simulation script was developed that sampled points on the surface and then iteratively found the steepest downhill direction. If paths of rainwater flowing on the surface ran into the gaps between the petals instead of into the valleys of each petal, the petal parameters were modified until the rainwater flows all ended at the central drains. The panel thicknesses were largely driven by building code requirements for concrete clear cover over the reinforcement, and by the current reality that concrete is reinforced by tying and placing rebar by hand. The concept for the reinforcement was to place the rebar in a fan-like pattern from the column base, emerging into the outer thinning field with reinforcement on the inside and outside faces. This reinforcement placement resisted the tension wherever it might occur within the shell. Within the column section, the full structural demand of gravity, wind, and live loading was concentrated and reinforced appropriately. In the field beyond the column, stresses were lower and the shell became thinner. Ultimately, the top edges were resolved with a 4-inch edge and the code minimum for adequate coverage of the reinforcement. In order to create a more seamless flow of space between petals, both across an arch and between adjacent half arches, the tangent of the surface edges were adjusted to align all surface curvature. This resulted in smooth transitions between petals despite the necessary 4-inch gap for the pin connections at the apex of each arch and the larger 16-inch gaps at the base of each column. So we saw this project earlier in the day, unfortunately, or one of them, which unfortunately collapsed. So once the design team had moved towards the use of concrete, it was assumed from then on that the formwork would need to be digitally fabricated to be able to achieve the necessary construction tolerances. In addition, it was assumed that fiberglass composites would be the ideal material for the formwork, as it was not only strong but very durable and could hold up to multiple castings. However, due to the contractual relationships between contractor and architects in the United States, in which the contractor is responsible for determining the ways and means of a project, the project's contractor, unfamiliar with digital fabrication or fiberglass composites, wanted to first get bids on traditional wooden formwork made from layered-up plywood. We only received one bid from a traditional formwork fabricator, and it was, in fact, larger than the entire project budget. So I thought I was going to be fired, or the project was going to be canceled at that point. But luckily, then the contractor agreed to reach out to our suggested fiberglass composite fabricator, Chrysler, and their bid was an order of magnitude less than the first traditional formwork budget, or bid. So this is an interesting example of a turning point within the industry. Historically, digital fabrication has been used in some of the largest and most expensive projects, while less expensive projects use traditional techniques. However, in this case, the traditional technique was far more expensive than the digitally fabricated fiberglass mold. In addition, the fiberglass mold was not only less expensive, but it was stronger, more durable, and more accurate. The three formwork modules for the A, B, and C petals were fabricated off of 5- and 7-axis milled EPS foam forms. After milling the forms, 2-inch thick composite structure composed of inner and outer layers of fiberglass composite with a central core of balsa wood was applied. As you can see, again, sorry. So basically, about an 1/8 of an inch of fiberglass was laid down on top of the foam form, and then this calendared balsa wood was laid over that could accept double curvature. and then another layer of fiberglass on the back to produce kind of a monocoque shell. Sorry. One of the biggest advantages of using this method was that the milled surface of the foam positive was highly accurate, and that all accumulation errors inherent in the fabrication were offset from the surface instead of working towards it. If we had used a traditional plywood formwork system, the CNC milled ribs would have been produced first, and then layers of plywood would be layered up from there, kind of accumulating error each time, so the largest error was closest to the final surface. Due to the size of each pedal formwork, which is the largest pedals were roughly 30 feet wide and 27 feet tall, each of the modules had to be subdivided into 3 primary subsections, in addition to several side forms that could be shipped to Texas from California by truck. Although the seams between these sections were nearly seamless due to the excellent casting of the fiberglass, the sanding, and small amount of caulk that was applied between the concrete pours, the seams were still designed to accentuate the undulating curvature of the concrete pedals. So if one looks closely, so you can kind of see there's one seam there, kind of undulating, and then another seam kind of in there. You can see another one there. All right. After the formwork was shipped to the site and positioned such that it could be cast as a modified tilt-up wall construction, the rebar was added to the formwork. Due to the curvature of the forms and the lack of a top form for most of the top side of the pedals, several tests were required before the right concrete mix was developed. The fact that the bottom surface of each pedal was cast against the smooth fiberglass while the top surface was cast open to the air allowed the 2 sides of the pedal to have radically different finishes. In order to have the pedals resonate with the flow of water, even when it was not raining, the open top side of each pedal was broom finished with the direction of the broom aligning with the flow direction of the water. In effect, the top surface of each pedal is one giant valley covered with a network of small valleys produced by the bristles of the broom. Over time, this textured surface of the broom finish concrete will reveal the flow of water as various airborne matter such as pollen, dust, and bird droppings collect on the broom finish and stain the concrete as water runs across the surface. So you can see here this laborer, it took a while to train them to broom the surface in the correct direction because it's not totally intuitive. When the whole pedal is tilted at a 45-degree angle, which is the downhill direction anymore. And they had to then build these brooms that had 12-foot long handles, and it's quite amazing to see. So, and this video shows, sped up slightly, this shows the lifting of 2 pedals. So each time we put an arch together, we had one crane first lift one pedal into place, then the other crane would lift its adjacent half arch into place. And I'm not sure how to, see if I can, it doesn't play. All right. So they were then lifted together, and while the crane was still lifting them, a pin joint was slid in between into the hinge, and then steel embeds that were on the bottom of each pedal, which you can see in the next image. Kind of right here, there's an embedded steel plate 1 inch thick that was then bolted down or welded to another plate, and then that plate was bolted, you can kind of see it a little bit maybe here, bolted to the ground, and that allowed us to, by adjusting the nuts on the bolts, we could adjust the angle of each pedal so that each one was perfectly true. And I should say, so this was the first arch erected. There are 3 smaller pavilions and then 1 larger pavilion. So this just shows how they are all structurally independent arches. Okay, so, this was somewhat interesting in that early on, so this was a rendering that I did, I think at the end of schematic design, and I had tried to convince the client that while the concrete was still, during casting, the workers would throw out little bits of iron onto the top surface of the concrete, so that over time the iron would rust with the rainwater, and we would get basically the structure would be painted with the flow of water over time with this rust color. So that's why it's white on the inside and orange on the outside. The client got really nervous about that, of like, telling them like, I'm intentionally going to rust your project. So they didn't do that. But what I find really nice is that the building has been up for a year and a half, and just like it's already starting to be stained by the water, just like I said, through the dust and pollution and bird droppings and so forth. Okay, having completed the project a year and a half ago, there are various things the team has learned in the process and have begun to speculate about how they might do similar projects in the future differently. So in terms of the material, a higher strength concrete with improved tensile capacity and uniform disbursement of reinforcement might be considered. So like I was saying, that we could have gone much thinner, but the code didn't allow us to go any thinner than 4 inches, because as we saw in the first lecture today, you need about 2 inches on either side of the concrete to keep the rebar from rusting away over time. So the building code limitations could have been challenged to allow thinner shells. However, the interest of this project by the public and the AEC community demonstrates a longing for the beauty of simple forms well executed. When a diverse team focuses on the smart application of new technologies and focuses on the integration of form, fabrication, and performance throughout the entire design process, innovative projects that meet the client's missions are possible even within modest project budgets. Thank you.
Thank you very much, Andrew. Can I ask all the presenters to join me here for our session?
Nice projects. Thank you. You too. It's beautiful. Okay. No, just
So thank you very much for 3 excellent presentations. I think it's really exciting work. To some extent, this session or panel was grouped as academia-industry collaborations. And I think usually what one associates with this is that projects are about efficiency, optimization. There are certain sort of economics attached to these projects. But what struck me very much in this presentation is that I think there's really a common thread through all these projects. And so I dare to say that there's a kind of perhaps striving for beauty and in design that's present across all the works. So my first question would be, within this collaborative setting, how do you communicate the value of design? And what is the value of design, and what does it contribute to these collaborations?
So on Confluence Park, I mean, each member of the design team definitely had that passion for bringing the beauty to the project and making that central. But I think every team has that. Like almost every architecture and engineering, like the reason we're in this profession is we kind of believe in that. The problem is often the client side saying, oh, well, yeah, that looks nice, but we can't afford that, or that's not our priority, something else. So in this project, what I think was the main driver was the client, where they were so secure in their stance that this had to be a unique project, and we had to keep on pushing the aesthetic bounds. So every time we would propose something, they were like, great, let's go further. And I had never kind of had that with a client, where they were just continually asking for more and pushing it instead of like holding back and like trying to spend less. I mean, the budget was $2 million. So it was a very reasonable project, but they kept on pushing for as much as possible aesthetically within that.
would say that in all of the projects that we've seen in this now, didn't design and function go hand in hand? I mean, there we had the function of it had to be tilted up, and we had the problem that we couldn't use too many formwork panels. Here we have the issue of that, the function of the pieces that they have to move. And for example, in the defabs lab, we had the issue of the forces that have to come down to a weirdly shaped wall underneath the slab. So in each of these cases, function and design were really going hand in hand, and I think that's also what makes them special. It's not a design that's then being thrown over the wall to the people that have to build it, which still happens a lot, but it's about moving function, design, and fabrication hand in hand.
Yeah, I mean, I think, is this working? Okay. I think the question is two parts. One about the presumption that the relationship with industry means that you'll focus on efficiencies, which I'm sure it's a loaded question, but I think if you find yourself having to argue for the merits of design principles, and you're losing energy by trying to force that argument over and over again, you're probably in the wrong kind of collaboration, because a collaboration that shares a respect for each other's contribution it means, I think it's inevitable. So, but the other part of the question is about beauty, and I don't know, like in our own work, we don't really have discussions about beauty, but we do have discussions about difference. And in thinking differently about things, so the alternative to efficiencies, like our default strategy is to add more mass. We don't try and remove mass, we just put more mass on the other side. And we found that to be a productive way of moving forward, and it charges difference in the things, because I think the default strategy in the construction industry, I wouldn't say industry at large, but the construction industry is that there's a presumption that we should remove things. We should remove mass and that lighter is better. Buckminster Fuller had the quote, how heavy is your building? But actually, like, I'm not seeing a whole lot of dome construction happening today in that manner. Like, so in that value, if you operate under the principle that efficiencies will trump every other decision, you're missing out on the potentials of alternative ways of thinking.
Yeah, I think that's evident in the projects and in the work. To follow up on the question of collaboration, what does constitute a successful collaboration, and what are the difficulties that come with it between academia and building industry or contractors?
Well, from my point of view, some sort of friction is always good. I mean, we want that, and I think both or every party involved wants that. It's about challenging each other. So if everybody would always be like, yeah, let's go ahead with that idea, that would be a weird type of collaboration. It always has to have some sort of friction happening in academia, design, industry, collaborations.
I also think collaboration is quite challenging, but very fruitful if the right people are on the table. So it's very important who you are collaborating with. And it's very important that you carefully select your collaborators, because you kind of want to work together and you will disagree in every collaboration, but if you have a vision that is similar, that's very important. If your visions are very different and your agendas are very different, collaboration would not be as easy, I guess.
A slight change of topic, something that was not specifically mentioned in the presentations, but is probably an underlying premise or discussion, is the question of intellectual property and the dissemination of knowledge. In your collaborations, how do you make that work, or how do you approach it?
The simple answer, contracts. The little bit more complex answer would probably revolve again around the vision of the partners. If it's about publishing papers, then it's just a matter of patenting it first and then publishing the paper, so that's rather straightforward. And if it's about a long-term vision that both want to achieve something together, then it's also about putting that in writing. What does that mean? That can be difficult, especially if very often you don't quite know what's going to be the result of your work together. So a basic level of trust, I would say, and a joint vision is then still very important in regard to intellectual property.
I mean, sometimes also intellectual property could be shared by more than one person. I remember in our slab project we had a material building science group within the university exploring with us what kind of concrete we can use, how can we mix it. But then at the other end we had Theo, our concrete spraying and casting partner, industrial partner, who was mixing material. And there was a point we said, like, can we share this mix within our paper? And there was all this discussion coming up. And the question is, okay, who owns what? Basically, at the end, the one who does the work will own that part of the project, I believe, right? But then those has to be clearly discussed in the beginning, and it's not always very clear.
Let me maybe add one thing to that. In my experience now with working with different universities and other partners, if we wanted to do the project together because we've seen that we have a common vision and a common goal, we've always found a creative solution to then also make it work in regard to IP and contracts and all of that. There's enough possibilities. So it's been a hassle every now and then with the lawyers, but it's worth the trouble to get that out of the way, and it's never a showstopper from my point of view.
Yeah, like there are the institutional challenges of the contracts and lawyers, but I think as a starting point, sharing intellectual property and authorship is the best way to start, because if you're not sharing that, you're not collaborating and in it together. If you're not sharing that, you're being hired to do something. You're not collaborating with someone.
I think I'll open this discussion up to the audience. At this point, I'm sure there are many questions. One popping up already. Where's the little catch box?
Yeah, thanks for the very interesting talks and very beautiful images. I guess my question is really for Brendan, but it's around the theme of what is an instrument, what is an architectural instrument, what is a tool. Because I've heard you several times self-deprecatingly say, oh, people say, what does this have to, is this not sculpture? Mm-hmm. And then you say, no, it's architecture. But I think that the proper comparison is with a tool. Is this not a tool? And I think the answer is yes, it is a tool for elaborating architectural techniques like stepping and pushing. Mm-hmm. And so I guess I would like you to talk more about how your project is not really about concrete. It's using concrete to elaborate a series of architectural gestures and tools and vocabularies and movement. And concrete is the proper massive thing with which to do that. Because, and perhaps this means you're kind of thickening the space of the user for spaces that you're not designing yourself or something like that. Does that resonate with your project?
Yes. I don't think that the core competency of our research is dedicated to concrete, but we collaborate with the concrete industry for their expertise. So if I break that out and to think about what is it that we're really invested in doing, it's in building reciprocity between how things are made and how we think about architecture. So, well, actually, one of the examples that's influenced me is Mark's experience with having conversations with stonemasons, and that we move away from the drawing and we start thinking about full-scale mock-ups of construction where the logic of how something is carved has an immediate reciprocity with how the geometry and the form is made. So I'd say that's the basic principle. And what's happened is that for us, it's expanded into thinking about the life cycle of how something is produced. So today, the contemporary construction site, for legal reasons, for all kinds of safety issues, we think of construction sites as being fenced off, hard hat only, specialty in there, and that we will wait for the building to be ready for us with the occupancy. But if we look back through history, there are other ways of thinking about architecture which is much more encompassing. There is a temple in Peru called Ollantaytambo, which was designed with the intention of having no completion date in sight. That it was continuously reconstructed. It was a laboratory for construction, and the Inca, the ruling class, was asking for revisions constantly because they needed to ensure that there was something to do for these master masons. That's a different way of thinking about architecture than the way we think today, but I think it would be wonderful if we could re-engage in topics of construction that engage community and society, such as Amish barn raisings or maintenance. Like, these are things that we have kind of pushed off to the other side. So this is something we're invested in today, and when we have conversations about who we collaborate with, it involves industry, but it also involves composers, chefs, like people that are invested in time-based media, for instance, that are challenging us to think in that way. I don't know if I'm talking about tools, but the way of thinking.
Maybe somewhat related, but for all the projects, because, as Lucia said, they're all very beautiful, and I like watching extreme sports like skateboarding sometime, you realize you always get the best shot, and they fell down a lot trying to do it. And I'm just curious, like, what were some of the fall down moments like, and whether, like, in the narrative that tip up construction, like, could be thought of as a process, how is that actually challenged by some of the barriers you had to overcome to actually make, like, the final sweet shot that you showed in the presentations?
I'll share two. I said in the lecture that there were several early tries to get the mix right. Unfortunately, when you're casting something that large, it's not like you can just do a slump test, down here. Like, it's the surface is changing curvature the entire time. The grid of rebars is differentiated. So in order to get the mix right, it actually took them 2 to 4 petals worth. And they were, unfortunately, we started casting with the smallest, which were only 17 feet high. So the first 2 that they cast and erected, the 17-foot high structure, there were holes in the concrete where the mix wasn't fluid enough. So holes big enough that you could see the rebar, that the rebar was exposed. And the contractor's solution was just to patch it. And the engineer and the architect and I, we were like, no, you cannot do that. Like, you can't just patch like a 4-inch hole. Like, over time, water is going to get in there, and it's going to fall out in someone's head, and so forth. And they weren't very happy about that because it meant they had to, jackhammer 20 tons of concrete out and recast them, and probably $100,000 worth of recasting. The second time they cast 2 petals, they thought they had a solution, which was after they demolded them and before the architects could get on site, they did a skim coat over the entire structure so that any of the holes, and then they sanded that skim coat. So it looked like just beautiful, like marble almost. It was just like super smooth, everything was perfect, and we were like, wow, you did it, like, this is amazing. And then we're like, wait, there are no air holes anywhere. Like, how did you do that? And they're like, oh, we just did a skim coat. We're like, you can't do that. Like, in 10 years, the water's gonna get behind again, and so forth. But at that point, they said, look, if you make us tear 2 more of these down, we're gonna quit. So the compromise is that if you go to the site, 2 of the, not of the main pavilion, but of the smaller satellite pavilions, 2 of them look really nice. But in 10 years from now, they might not.
Yeah, I also would like to share a lot of our experience, but I think the time doesn't allow. But our project took 3 years of constant design prototyping, discussing with industrial partners and the collaborators within the project. And the prototypes that I showed, the slab prototypes that I showed in the beginning were the earlier prototypes for the ceiling, that then the ceiling came, they looked very different. The design looked very different. The fabrication method eventually looked very different. A good example is initially we wanted to have a stay-in-place formwork because we could be more complex in our shape and really express the potential of 3D printing. But once we went to city and tried to get this done, they said, well, you have to check if how stable is this sand on the concrete. How long does it stay? Is it gonna crack after 5 years? Then once we figured out, no, actually it can't be there right now. The technology, it doesn't, the bonding is not enough for it to stay for a long term. We had to rethink the formwork and redo the entire formwork system, also the design accordingly. So there has been a huge resources in prototyping and large-scale prototyping, which you could not replace with small tests, basically.
A couple of, things that went wrong with the big concrete piece we did there is we usually calculate where to attach the crane to such a big formwork piece. Now we had some 3D printed forms on there, and nobody really did the measurements about how much would that weigh now and where should we now attach the crane. So you pick up this huge piece of formwork and it lifts up, and all of a sudden all the weight is on one corner, and that corner was made out of wood. So it didn't quite last that. So we had to pick it up off the ground, then repair it while it's hanging on the crane, and then put it back down again. So that was the things that we usually think of when we design these big pieces. But in this case, nobody really considered the change of the weight, which afterwards is like obvious. Yeah.
We've never, I don't know, our things always work. We've obviously broken a lot of concrete.
No broken toes?
No broken toes. There's safety, safety. I think what's been interesting is we do work with the stone industry as well, and they obviously have experience with moving big, heavy things, and things that you think will be safe are very much not safe. So the rule is anyone that tries to stop a stone from falling over doesn't survive to tell the tale. So especially when dealing with students, because we are doing experiments, it's distance first, like let's get away. But sometimes we have failures that are really instructive, that tell us a great deal about the behavior of the object, and other times we have failure for dumb reasons that don't inform anything. It's just process and things get messy. But I find it interesting, coming from the engineering field, like this is obviously testing to failure is something that you're well trained in. I feel every time we collaborate with a structural engineer, all they want to do is just break what we've made. That's all they're interested in doing. So they just show up right before the exhibition and they're ready to break it,
Thank you. My question is about the formwork for concrete, the sand casting. I don't know whether you are aware of those. The example of the sand casting that I know of in the United States is Arcosanti, and all the concrete there is sand cast concrete, huge arches and vaults and so forth and so on. That's my question from you. And the other one from the gentleman with the heavy movements. Even though that is a, how should I say, a way of looking at architecture, there are similar ways of looking at architecture. For example, the temple, Ise temple in Japan, where you leave the temple to live, to deteriorate, and you build another one 20 years later. So that, and nature is itself goes towards this sort of entropy and the less weight. So what Buckminster Fuller was suggesting is a way of looking at a principle.
Yeah, so I didn't really understand the question. Sorry, do you hear me? I didn't understand the question about sand casting of the concrete in that place. What is the question exactly? Sorry.
But have you looked at the sand casting? Because this fiberglass with all computer and so forth is high tech. Sand casting is low tech.
Is it? Low tech. Oh, in that sense. Well, I mean, I don't know if I can tag it as a high-tech versus low-tech, but definitely sand casting, or let's say there was a lot of project within the history where you have bricks and you cast in, or you have sand and then you cast into strength the area. Those are very different project than this, in a sense that this one is a prefabrication of formwork and prefabrication of lightweight concrete elements that you would then bring to the site, if that.
No, those pedals, the pedals that we were talking about.
Oh, sorry.
Or both, but the pedals, it's you lift them and so forth. There is no in sand casting. You just make it on the ground.
I mentioned that with tilt-up concrete, one of the there have been examples where they would dig into the earth to create like a curved mound of earth and then cast concrete against that and then tilt it up from there instead of tilting against a flat earth plane or a flat slab. But one of the issues, like I said, was about modularity and that we needed to have a high level of tolerance and be able to cast 28 petals off of only 3 forms. So those forms had to be reusable very, very quickly, the turnaround time from one cast to the next. And if you had used sand, it would have been very, very difficult to make sure that one mound of sand was identical to the previous mound of sand. And if they weren't, none of the petals would fit together.
Okay.
I don't know if it is a question.
Yeah.
Do we have another question from the audience?
Whoa. I think that something that I often hear about projects like this regarding sort of material research and industry application is always asking, how do you plan to scale this work? How do you plan to apply this later? Which I think is maybe a little reductive sometimes. I'm wondering sort of how you all position these projects within sort of a larger scope of research, how you might understand this individual effort in terms of your longer track of research or of making or of potential application, sort of without asking what do you plan to turn these into, sort of how do you understand these own projects in terms of your own work?
Real quick for me, one of the things I've struggled with since starting my practice was how to grow the practice. There's the founder's dilemma that you're probably familiar with, where you start a business because you love what you do, and then you're successful in that business, and then you have to grow the business, but then you end up just being in meetings and email all day long and not doing what you started the business to do. You've hired other people to do that. So I've always struggled with that in my practice. So one of the things that Confluence Park has helped me to realize was the value of collaboration. Like, rather than thinking that I needed to grow my office and to have all of these numbers of people like under me, that wasn't productive because I wasn't going to enjoy it. That collaborating with others allowed me to go to another scale where other firms who were experts at project management or the engineers and all of that now I realize how I can grow my practice in a way that I hadn't before. And I think that has to do a lot with the way that we teach architecture, that I think there's a tendency to to teach architecture as if every student is going to start their own practice and become a celebrity architect. And I think a much more productive way of teaching would have, similar to what you probably went through at ETH, that this is the power of collaboration between a really multidisciplinary team.
Yeah. Did I understand the question right? That you want to know how this impacted our research trajectory, right? Kind of. I mean, or how we define our research accordingly. But like for me, these were a stepstone of the research. So these are the research. I think the first day that we started this project, I couldn't even believe that we could make a real slab out of sandstone formwork myself. I mean, like I thought it was a dream. Like I was like, oh, we're going to talk about it and we're going to convince the contributor to work with us. And it was such a dream that, but then you have to research throughout to make it happen. And when it happens and it's the final result, that's really a demonstrator of a very long time research through which we advance a lot of computational method, through which we advance a set of fabrication methods. And we learned a set of material processes that we didn't do before. So I guess by just doing them, we did the research through them. Yeah.
Well, for us, scalability is key for us, obviously. Usually when we get contracts, I mean, I've shown you the picture of in Columbus, Ohio. I mean, that's a couple of thousand square meters of free-form formwork. So scalability is key, and I think we can do that today. The 3D printed parts are still rather expensive, but I mean, the price is dropping every year, so that's good. But what we've heard, I mean, the formwork industry doesn't really have a very good image. We've heard, for example, the quote that you got. I don't want to know who you got it from, but that's, and so, I mean, our mission as a company is to make building for our customers, contractors, builders, designers, faster, more efficient, and more safe. And all what we're doing is tailored towards that ultimate goal. So that's our problem. And I think if now we want to hand over this technology and show new potential, what happens more often than not is we get a design that people want formwork for, then we tell them the price tag, and then usually they change the design because the formwork is so expensive. And that needs to be changed by us. I mean, we need to make sure that these not only beautiful designs, but also functionally appealing designs are not limited by the formwork solution. And that's what it's all about.
I mean, I think for industry, it's a rather straightforward question of like the nature of scaling, and then the cliche in architecture, and I sympathize, Andrew, with your point, is that you can either scale the project or you scale your practice. Beginning installations, residential, like building bigger buildings. I think the way that we have to think through research is scaling impact. And sometimes the best value to scale that impact is by scaling the project itself. Another way of scaling impact is by moving into another media to be able to disseminate that knowledge. And if we can convince other people to change their minds about their behavior, then we're being successful. I think that's another way of thinking about scaling. So for instance, we did a research project on cannibalism of stone rubble and produced a cookbook and disseminated that to the world, asking other people to do it, because we are not interested in getting into the recycling of concrete game ourselves. So I think that question of scale is something that we always have to address and to ask ourselves, what is it about this project or this way of thinking that will scale best?
Okay. Thank you very much again for the presentations and this great session. Unfortunately, we're out of time and we need to move on to the next one, but thank you guys.